Energy is a fundamental concept in physics. It is the driving force behind all physical processes and phenomena in the universe. Without energy, nothing would move, change, or function. From the smallest particles to the largest galaxies, energy is at the core of everything. It allows us to describe and predict how physical systems change. By understanding energy, we can make sense of the natural world and harness its power for various applications, from powering our homes to exploring outer space. The most important thing to remember about energy is that it is always conserved. This principle, known as the conservation of energy, is a fundamental law of physics that applies to all systems, regardless of their size or complexity. This means that energy cannot be created or destroyed. It can only change forms, moving from one type of energy to another. For example, the chemical energy in a candle's wax is converted to light and heat energy when it burns. It can only be transferred from one form to another. This transfer of energy is what allows us to perform work, power machines, and sustain life. Imagine a roller coaster car climbing a steep hill. The car's engine does work to move it uphill, converting electrical or chemical energy into mechanical energy. The car's engine does work to move it uphill. This work is a transfer of energy from the engine to the car, increasing its potential energy as it gains height. This work is a transfer of energy from the engine to the car. As the car climbs, its potential energy increases, storing energy due to its elevated position. As the car climbs, its potential energy increases. This is the energy it possesses due to its position, ready to be converted into another form. This is the energy it possesses due to its position. At the top of the hill, the car has a lot of potential energy, which is the maximum energy it can store at that height. At the top of the hill, the car has a lot of potential energy. As it begins to descend, this stored energy starts to convert into another form. As it rolls down the hill, this potential energy is converted into kinetic energy. Kinetic energy is the energy of motion, and it increases as the car speeds up. Kinetic energy is the energy of motion. The faster the car moves, the more kinetic energy it has, demonstrating the dynamic nature of energy transformation. The higher the car's speed, the greater its kinetic energy. Throughout the roller coaster's ride, the total energy remains constant, illustrating the conservation of energy. Throughout the roller coaster's ride, the total energy remains constant. Energy is transferred between potential and kinetic forms, but the total amount never changes. Energy is transferred between potential and kinetic forms, but the total amount never changes. This seamless transition is a perfect example of the conservation of energy in action. This is the essence of energy conservation. Understanding this principle helps us appreciate the interconnectedness of all physical processes and the unchanging nature of energy in our universe. In physics, work has a specific meaning. Work is done when a force causes a displacement. In other words, work is done when a force makes something move. Think of lifting a heavy box off the ground. You exert an upward force on the box, and the box moves upward. You have done work on the box. The amount of work you do depends on the force you apply and the distance you lift the box. Work is a way to transfer energy. When you do work on the box, you are transferring energy from your muscles to the box. This energy is stored in the box as gravitational potential energy. Sankey diagrams are a useful tool for visualizing energy transfers. They show the flow of energy through a system, from input to output. Imagine a light bulb connected to a battery. The battery is the energy source. It provides electrical energy to the light bulb. The light bulb converts some of this electrical energy into light and some into heat. A Sankey diagram of this system would show the electrical energy flowing from the battery to the light bulb. The diagram would then split into two branches, one representing light energy and the other representing heat energy. The width of each branch would be proportional to the amount of energy it represents. As mentioned earlier, work is directly proportional to both the force applied and the displacement of an object. This means that the amount of work done increases as either the force applied or the distance over which the force is applied increases. This relationship can be mathematically expressed as work equals force times displacement times cosine of theta, where theta is the angle between the force and the displacement. The formula is often written as W equals sine F cos. This equation helps us understand how work is calculated in different scenarios. Consider pushing a box across a floor. When you apply a force to the box, it moves in the direction of the force. The work you do depends on the force you apply to the box and the distance the box moves. For instance, if you push the box with a small force, it might not move very far, resulting in less work done. If you push the box with a greater force, you will do more work. This is because the work done is directly proportional to the force applied. The harder you push, the more energy you transfer to the box, causing it to move further. Similarly, if you push the box over a greater distance, you will also do more work. The distance the box travels is a crucial factor in determining the total work done. The further the box moves, the more work is accomplished. It's important to note that work is only done if the force and displacement are in the same direction. If the force applied is not in the direction of the displacement, no work is done in the context of physics. If you push a box horizontally across the floor, you are doing work. The force you apply is in the same direction as the displacement, resulting in work being done on the box. However, if you carry the box across the room at a constant height, you are not doing work on the box. This is because the force you apply to hold the box up is not in the direction of the displacement. This is because the force you apply to hold the box up is perpendicular to the displacement of the box. In such a case, the work done is zero because the force and displacement are not aligned in the same direction. Section 5. The mechanical energy trio: kinetic, gravitational, and elastic. Mechanical energy is the energy associated with the motion and position of an object. It has three main forms: kinetic energy, gravitational potential energy, and elastic potential energy. Kinetic energy is the energy of motion. The faster an object moves, the greater its kinetic energy. Gravitational potential energy is the energy an object possesses due to its position in a gravitational field. The higher an object is above the ground, the greater its gravitational potential energy. Elastic potential energy is the energy stored in a stretched or compressed spring. The more you stretch or compress a spring, the greater its elastic potential energy. Section 6. A world without friction: ideal mechanical energy conservation. In an ideal system with no friction or other non-conservative forces, mechanical energy is conserved. This means that the total mechanical energy of a system remains constant, even as energy is transferred between kinetic, gravitational, and elastic forms. Imagine a pendulum swinging back and forth. At its highest point, the pendulum has maximum gravitational potential energy and zero kinetic energy. As it swings down, its potential energy is converted into kinetic energy. At its lowest point, it has maximum kinetic energy and zero potential energy. The pendulum then swings back up and the process repeats. Section 7. Energy transformations in action. Energy transformations are happening all around us. Every time something moves or changes, energy is being transferred from one form to another. Consider a bouncing ball. When you drop the ball, its gravitational potential energy is converted into kinetic energy. As the ball hits the ground, its kinetic energy is converted into elastic potential energy as the ball deforms. The elastic potential energy is then converted back into kinetic energy as the ball rebounds. This process continues, with energy being transferred back and forth between potential and kinetic forms until the ball eventually comes to rest. Section 8. Power, the rate of energy's flow. Power is the rate at which work is done or energy is transferred. It tells us how quickly energy is being used or generated. The unit of power is the watt, which is equal to 1 joule of energy transferred per second. For instance, a 100-watt light bulb uses 100 joules of electrical energy every second. A powerful car engine might generate hundreds of kilowatts of power. Power is an important concept in many areas of physics and engineering. It is essential for understanding the performance of machines and the efficiency of energy conversion processes. Section 9. The efficiency factor, making the most of energy. Efficiency is a measure of how effectively energy is transferred or converted from one form to another. It plays a crucial role in determining how much of the input energy is actually utilized for the intended purpose. In various industries, from power generation to manufacturing, improving efficiency can lead to significant cost savings and reduced environmental impact. No energy transfer is perfectly efficient. There are always losses involved, primarily due to factors like friction, resistance, and other inefficiencies in the system. These losses can be particularly pronounced in older machinery, which may not be designed with modern efficiency standards in mind. Some energy is always lost as heat due to friction or other factors. This is a fundamental principle of thermodynamics, where energy conversion processes inevitably produce some waste heat. In industrial settings, managing and minimizing this heat loss is a key challenge. Efficiency is usually expressed as a percentage. This percentage represents the ratio of useful output energy to the total input energy. For instance, an efficiency of 50% means that half of the input energy is converted into useful work, while the other half is lost. A process with 100% efficiency would mean that all the input energy is converted into the desired output energy. This is an ideal scenario and is practically impossible to achieve due to inherent losses in any real-world system. However, this is never the case in real-world scenarios. Real systems always have some degree of inefficiency, whether due to mechanical friction, electrical resistance, or other factors that cause energy loss. For example, a car engine might have an efficiency of only 25%. This means that a significant portion of the energy stored in the fuel is not used for propulsion, but is instead lost as heat and other forms of waste energy. This means that only 25% of the chemical energy stored in the fuel is converted into useful kinetic energy to power the car. The rest is dissipated as heat, sound, and other forms of energy that do not contribute to the car's motion. The remaining 75% is lost as heat. This inefficiency is a major factor in the overall energy consumption of vehicles and highlights the importance of developing more efficient engines and alternative propulsion technologies. Improving energy efficiency is a major focus in many fields, as it reduces energy consumption, costs, and environmental impact. Advances in technology such as energy-efficient appliances, renewable energy sources, and improved industrial processes are all contributing to a more sustainable and efficient future.